Okay, so welcome everybody to the final day. The first speaker is Francesco Cellarosi. We'll talk about the Jacobi theta function near the real.
Thank you. Thank you very much to the organizers for this opportunity to speak. Can you hear the microphone okay? Thank you. So thank you for the organizers for the opportunity to speak. Among the organizers, I would like to single out Marco, who's also been a great host in the past 3.5 months for me in Bologna. And I would like to thank all of you for being here this morning to attend a talk whose title has no dynamical appeal whatsoever. So hopefully I'll convince you that there is some dynamical ingredients, and the title actually is more of an excuse to illustrate a recent result in a more general setting. What I'm going to talk about today is joint work with Tariq Osman, who's here and will actually be the second speaker of the morning. So let's get going. So I want to start by describing the main object of interest here. We're looking at a sum, Sn, that depends on a bunch of parameters. So x, alpha, and beta are real numbers, and they're all features in this exponential term. By e, I mean e to the 2 pi I here. So this is a complex exponential. So these are complex numbers of modulus 1. And then I somehow weigh this sum by this kind of weight function f. To keep things simple in your mind, you could think of capital F as the indicator of an interval 0, 1. And in that case, the sum, instead of being over all of the integers, simply breaks down to a sum from 1 to capital N. Right? So if you want to, in your mind, think of F as an indicator, and so this is just a finite sum. In fact, we will actually require F, for the purpose of this talk, to be smoother than that for technical reasons. But you think of F as some kind of smooth indicator. The goal that I have is to think of X as random, or later on, actually, X will be arbitrary. But think of X as random and alpha and beta fixed, as I mentioned down here. And then when X is random, you let N go to infinity. So you think of these as a sequence of complex valued random variables indexed by N for alpha and beta fixed and X random. And then you want to understand how these random variables in the complex plane are distributed as N goes to infinity. So you want to study the so-called limiting distribution of this family of random variables. Maybe I should say a few words about why should we care about these particular sums or these particular expressions. Well, they appear naturally in this. I didn't prepare a slide for the motivation, so I'll just tell you. They appear naturally if you study certain problems in quantum mechanics, for example. You may have, so for example, if you take alpha equals 0, if you take alpha equals 0, there are quantum mechanical systems whose eigenvalue, so where the eigenvalues of your operator are exactly quadratic polynomials, and if you choose f of a particular form, this expression basically represents autocorrelation functions. You can think of x in this case as time in your quantum operator. And so there is a way of representing autocorrelation functions via these exponential sums. Another place where they appear naturally is in some problem of optics. If you study some diffraction patterns generated by certain gratings, where you have a screen at a certain length, you have a certain width of the grating. There's a bunch of parameters in the system, and in some limit, these are natural objects to study. Also, if you study gap distribution between quadratic expressions like these, then, and you can, like in the talk by Jens Markloff, if you look at all possible differences of all possible pairs of quadratic expressions, and then you look at the empirical measure on all the possible gaps, and then you take the Fourier transform of that, you get something related to these exponential sums. So these exponential sums appear naturally in a lot of dynamical and or number theoretical and physical mathematical physical contexts. So what's the summary of what's happening in the context of this problem that I mentioned earlier? So there's a different behavior depending on what alpha and beta are. And as I said, alpha and beta are fixed. You could make them random together with x and the problem becomes easier. But if you fix them, then the problem becomes more subtle. So if alpha and beta are both, let's see. Did I lose this? Okay. If alpha and beta are not both rational, so if at least one of them is irrational, then the limiting distribution, as I described before, exists and has heavy tails. So in the complex plane, you get a limiting distribution with up to 6 but not 6 moments. So the tails are heavy. This was studied in a joint paper with Jens Markloff and in a more recent paper where we, with Jory Griffin and Tariq Osman, where we actually look at more general expression, not just one of these SNF, but SNF1 times SNF2 bar, let's say. And then you look at the distribution of those for F1 and F2. And we actually improved explicitly the tail bounds. So we know the leading term of the tails, this r to the minus 6, if you look at the probability of being outside the ball of radius r. And then we also have an explicit error term of what comes next. So we have very good tail bounds when it comes to understanding the powers. But then, so this was somehow settled. Then, the rational pairs is what's left. So in the rational pairs, there is a Starkin dichotomy. Either, for example, if you take alpha and beta both equal to 0, and that was done in an older paper by Jens Markloff in 1999, if you take, for example, alpha and beta both equal to 0, then you still get a limiting distribution that has heavy tails, but the tails are heavier. So now you have up to 4 moments, but not 4 moments. And what I should also mention is that in the irrational case, no matter what irrational pair or like not both rational alpha and beta you choose, you get always the same limiting distribution. So there is some kind of universality in the irrational case. But in the rational case, if you have heavy tails, for example, in the case 0, 0, the constant in front of the tail actually depends on alpha and beta. So you lose this kind of universality, and there is more of a number theoretical phenomenon. So either you have heavy tails, but heavier than in the irrational case, or quite the opposite, you have a compactly supported limiting distribution. So in the irrational case, there is a stark dichotomy. So in the case of a compactly supported limiting distribution, after we realized, and I was personally surprised when I saw this, after we realized that there is this compactly supported limiting distribution, then we were like, okay, let's try to understand this before we take n to infinity. So can we prove that these things are just bounded for every n? And that's what I've written here. And that's what I want to talk about today. So in the case of parameters alpha and beta for which we know that there is a compactly supported limiting distribution, we actually prove something stronger here. We prove that there is a uniform bound that holds for every x and for every n. And so in particular, when you take n to infinity and you normalize by root n, of course you get something compactly supported, right? So this is a stronger statement than the one written in green here. So that's the one I want to focus on today. And I should mention that in the case alpha and beta both equal to a half, this was already discussed by Markloff in a paper in 2008, but the 1/2 case is somehow special in a way that I'll explain later. So here, when I write ... is whatever rational pairs don't give you compact support, they will give you the heavier tails. All right. Yes, of course.
So the distribution doesn't depend on x, for example, in the first statement?
No. It doesn't even depend on how you sample x. X could be sampled uniformly in an interval, could be sampled with a Gaussian, could be sampled with a Cauchy distribution. Whatever sampling distribution, as long as it's absolutely continuous with respect to the Lebesgue measure on R that you choose for x, it disappears in the limit. So there is even that level of universality. But in the rational case, even the sampling distribution should matter when you look at the values in the complex plane. But here in this case, we're just looking at the absolute value, the distribution of the absolute value, because we're only looking at tails. And so in that case, it doesn't matter. But if you look at the genuine distribution of the complex plane, and I'll show you some pictures, then even the sampling distribution should have an effect in the rational case. So the rational case is very delicate in a sense. It's less universal. That's why we left it for later investigation. And now somehow this completes some of the understanding of this quantity. So here I recall for you what the definition of this sum is, and I give you our theorem. So the theorem is that if you choose alpha and beta rational, of course they have to be rational for there to be something interesting that wasn't known before, but you choose them of a particular kind. You choose them as odd divided by twice an odd number, and then odd divided by twice an odd number. Those are my choices of alpha and beta. And you choose them so that the GCD of A, B, and M are all is 1. It doesn't mean that these fractions are both reduced in lowest term, so one of them may not be reduced, but this is a condition. So for example, 1 over 2m, 1 over 2m works. That's the kind of prototypical example that you should think of. You fix a function of Schwartz class, and again, as I mentioned later, this can be relaxed. Then there will exist a constant that only depends on the function and on this denominator m, so that no matter what x is and no matter what n is, these sums are bounded by constant times root n. So it's a bound of size, it's a big O of root n kind of bound. Here I mention for my convenience later, in case I get to discuss some of the technical parts of the proof, the more dynamical parts of the proof, I mention here that there is a tool or a quantity that we use to investigate somehow the decay and the regularity simultaneously of this function. So you imagine you have a quantum harmonic oscillator. So you have a PDE of this kind, a Schrödinger equation of this kind, where f is your initial condition. At time 0, you have f, and then you let it evolve for time t, and at time t, it satisfies this equation. So what we require is that this, the function, the evolved of the function, imagine there is a unitary operator that evolves your function from time 0 to time t. The evolution of your function for time t has some amount of decay. So you multiply by 1 plus u squared to the s over 2. So this quantity, the sup over both t and u, should be finite. And we want s to be at least 1. So if you take Schwartz functions, this will be true for every s. If you take the indicator that I told you at the beginning, this will be true for s equal to 1. And in particular, this doesn't hold. No, here it's not. That's what I said. Exactly. So the general goal was to understand this kind of limiting distribution. But in this case, we actually prove a bound that holds for every x and implies the fact that when you sample it randomly, of course, you get a compactly supported limiting distribution. So this is a stronger result in a sense. Well, it depends, right? So you can have, if x is equal to 0, then because this is rational and not 0, alpha is rational and not 0, it's like this is going to be O of 1, actually. This is going to be a sum that's just bounded, not even O of root n. Right? So it is true that these sums could be actually O of 1. Because there is so much cancellations, if you put x equal to 0, you just get, I don't know, 1 over 6. And then so somehow you're summing over. I mean, this is the Gauss sum. X equals to 0, right? Well, it depends on your weight function, right? If f was the classical indicator, then it would boil down to a Gauss sum. But this is a slightly more general kind of weight. Yes. So somehow this is to say that we could somehow relax this condition that f is Schwartz if we assume some kind of uniform control on the solution of a quantum harmonic oscillator. So this is the first somehow dynamical aspect, technical aspect of these results. And as I mentioned in the previous slides, we can actually prove this in a more general setup where you don't just have one function, but you have f1 and f2, and then you look at Sn f1, Sn f2 bar at the same parameters, and you get exactly the same result, but now the constant will depend on f1, on f2, and on m. Yeah, but for the purpose of the presentation, I'll just stick with one function. So a third remark, so this is the same statement, just a third remark, is that getting bounds that hold for every x, like you mentioned, is very strange. It's very unusual to get bounds for every x. And as I say here, unless alpha and beta are very special, and by very special I mean this particular arithmetic condition, typical bounds that you get for sums like that either hold for typical x's or for exceptional x's. So here to mention, you can see here lots of names, and you can recognize a lot of names of people that are highly dynamically minded. So just to mention some results that go to Markloff or Markloff and Welch, if you want a bound that holds for every x, then you can get a bound of this type where you have a root n and then some power of log n. It's actually a subtle result because first you choose gamma not too large, and then you can find a full measure set of x's for which this bound will be true, and it will be true uniformly in alpha and beta. In the particular case of f equal to an indicator, there's been a lot of other works, and I should mention, for example, down here, the work of Flamini and Forni or Fedotov and Klopp, where here I'm really underselling their results, because here I'm somehow simply saying that you randomly choose x and alpha, but it's actually more subtle because, I mean, this is true, but the result is actually stronger because you can say, if you give me alpha, then I can find a full measure set of x's which depends on those alpha, and for those x and alphas, I can get a bound again of this kind. So, and again, it doesn't have to be a power of the log. It could be like a function of the log with the function has a certain growth. But what I wanted to stress here is that typically you don't get control of every x. You get control for almost every x. Or if you make a very stringent assumption on x, for example, x is of bounded type, so the continued fraction expansion of x as entries that are bounded by some constant, then you can get a bound of this kind. And these bounds were all for either beta wasn't there, or you fix alpha, but beta is specifically equal to 0. There is some old results of Hardy and Littlewood, and I also mentioned here some references that deal with sums of this type in a higher dimensional setting, where you could imagine replacing this quadratic polynomial up here by a quadratic form in several variables. So some of these results, like Markloff and Welch, Cosentino, Flamini, and so on, some of those actually deal with the higher dimensional case. And I really think that there should be a higher dimensional version of this result as well. And I'm convinced that that should be the case. So hopefully I've convinced you that there's been enough interest in this kind of sum. So let's get into an application. Maybe next to your first year book in ergodic theory, you have a first year book in several complex variables. So it's a classical function to study of two complex variables is this Jacobi theta function. So the Jacobi theta function is a function of two complex variables, zeta and tau, where the imaginary part of tau is bigger than 0. And it's defined in this way. So it's a sum over all the integers of e to the pi I n squared tau, e to the 2 pi I n z. So maybe here you see, because for historical reason there is a 2 pi I here and there isn't a 2 pi I here. That's why we somehow artificially put this 1/2 in here, just to be this 1/2 here seems like an artificial choice, because you put a e to the 2 pi I and then you do a 1/2 n squared. So the reason we have this normalization 1/2 here is somehow to be consistent with this kind of more historically solidified notation, where one of these variables has a 2, the other variable doesn't have a 2. So there's nothing special about that 1/2 we had there. If I rewrite this function, instead of in the variable tau, I write it in the variable q, which is e to the pi I tau, then this is not quite the same thing, but I'm abusing the notation, right? I'm thinking of this tau as a function of q or vice versa. then is a more classical way of writing this expression. And you can see that this function converges only for q of modulus less than 1, strictly less than 1, which corresponds to exactly the imaginary part of tau strictly bigger than 0. And I will stick to this somehow setup because I will work in the upper half plane. But sometimes it's better to think about the radius of convergence of this power series is, if you look at them, you can realize that there is a dense set of singularities near the boundary of this disk at q of modulus equal to 1, which corresponds of tau on the real axis. And because you have all of these bad singularities near the boundary, you cannot continue the function outside this disk. And that's why I want to talk about this function near its natural boundary. The boundary is there, and it's given to you by this expression. Here you have two pictures of the real part and the imaginary part of theta of q. Q again is in the disk when z is 0 in this particular case. So you can see all these singularities near the boundary. So now let's do a computation. I told you that we can handle sums like this. Now let's pick a particular function f, which is a Gaussian, e to the minus pi u squared. If you plug in the definition of Sn, that Gaussian, so here is just plugging into the definition, and then you gather this expression with the 1/2 n squared, and you really think of this minus as I times I. So you put I here and another I here. So if you do the computation, you can recognize exactly a Jacobi theta function evaluated at z equal alpha plus beta x, and at tau of the form x plus I over n squared. And you have this normalization n to the minus 1/2 in front of it. So now I somehow changed names of my variables. I call epsilon equal to n to the minus 2. And so I'm really looking at the Jacobi theta function where the variable tau is near its natural boundary. Think of epsilon equal to 0 giving you the natural boundary as we discussed. And then somehow the other variable z is somehow tied to the real part of tau. So you see that x is the point in the coordinate and that I'm approaching on the boundary, and here the alpha and beta times x gives me an affine function of x that I somehow force on the other variable. So I'm fixing one variable as kind of a function of the other. And because of our result, we can understand how this function behaves near its boundaries, and when epsilon goes to 0, for a particular choice of z, which is exactly the form alpha plus beta x. Very well. So let's rewrite our statement in terms of this particular case. Again, you have alpha and beta. Here I take them for simplicity in the interval 0, 1. That doesn't have to be. So I choose A, B, M of this kind as before. Then there is going to be a uniform bound that only depends on M of this type. So this is giving you a way of controlling how somehow the blow up of this function near its boundary occurs. So here, this is telling you that at least along these lines, you get, the pointer is gone. At least along these lines, you get this control, this blow up that's no more than epsilon to the minus 1/4, and it's uniform in x and epsilon. This set of parameters, alpha and beta, that we describe in this corollary, you may think, is it very rare for this to happen? Is it very exceptional? Well, how can we measure that? Well, if you look at the possible rational pairs with denominator equal to 2m in the torus, so there will be 2m squared of them, so there will be 4m squared of them, and you can count how many of them there are that actually satisfy our condition, and you can see there is a function, an arithmetic function that counts these things. These are also called Jordan-Tottian functions. Like this is the second Jordan-Tottian function for the number theoretically oriented people. And here is a count of how many such pairs there are for given m. And you may realize that this quantity grows kind of approximately like m squared. There is actually a lower bound and an upper bound of how big this quantity is in terms of m squared. So there's going to be m squared no more than a constant times m squared, and no less than a constant times m squared many pairs. So among these 4 m squared many possible pairs, there is a lot of them that satisfy this condition. So it's a positive fraction of them. So here is a picture where I show you in light blue. I hope you can see the light blue. All the pairs with denominators 2m for m equal to 1, 3, 5, 7, 9, 11, 13, and 15. And I select the one that are colored in dark green, those that actually satisfy our result. So you can see that there is some interesting structures of like some dots that you see could be there, but they're kind of missed. Like you see here, but you see definitely some interesting structures in these points. And I hope to convince you that these pictures are actually orbits under a certain action, and understanding these orbits and understanding the geometry of these orbits is somehow a key dynamical aspect of our analysis. All right, so let's see. So here, let's look at, for example, at the case n equal to 9 in the bottom corner. So there is 72 pairs of rational numbers that satisfy our theorem. So that gives me 72 affine relations between z and x, because for each of those alpha and beta, I can choose an affine function. So here I plot z as a function of x. There is 72 such lines. So there is 72 affine curves along which, when I plug them in here, I get the same bound for all of them. This constant works is the same constant that only depends on m, in this case 9, and it works for all of them. So you get simultaneously a lot of bounds of the same quality for a lot of choices of z as an affine function of x. So this is just a picture of how these, in this particular example, how these pairs depend, how they look, like how these functions look. So these are all a over 18, b over 18, where a and b are odd, and the GCD of a, b, and 9 is 1. So this is, and then I plot all of these functions. Okay. So here, now I have 72 ways of doing this. So now I do it. Now I take the 72 values here, I plug them in here, and I plot this theta as a function of x for fixed epsilon. So in the next slide, I fix epsilon, 1 over 16, and then I plot simultaneously these 72 functions, or the absolute value of those 72 functions. And you see, I put the epsilon to the 1/4 together with the function, so I expect everything to be bounded. And you see that these functions, look potentially very complicated, but they're all bounded by, they're all capped at the same value. The value is slightly less than 2. So now, what I'm going to do, I'm going to change the epsilon. If I change the epsilon, I should expect that this bound that caps all of these functions doesn't change. But the function will become more complicated because the bound that I have doesn't depend on epsilon. So now I do exactly the same picture for the exact for the same 72 choices of alpha and beta, but I change the epsilon. If I do it, I get much more complicated pictures. The bound is still less than 2. You see in the scale there's a 1.5. Now epsilon is much smaller, but the kind of uniform bound is the same. Okay, so this is the kind of illustration of our result. All right, so now that I've convinced you that somehow there are some pretty pictures related to this result, I want to go back to the general result where f doesn't have to be the Gaussian that gave you the Jacobi theta function, and I want to somehow illustrate several steps in the proof of our bound. The first step, which is somehow in a sense the most mysterious in my presentation, is to come up with a function capital C, which depends on f. F is my weight. Think of, again, the Gaussian in the particular case of the Jacobi function, so that this suitably normalized, this thing stopped working. This suitably normalized, I don't know, maybe I can point here. This suitably normalized sum will be written as the evaluation of some function, capital C, which depends on f only, along something that looks like psi x, phi t. So we had, luckily, we had several talks in the past couple of days, the one by Jens Markloff, by Mark, by Peter. So we had several talks where this kind of setup appeared, maybe not quite in this generality, but you basically have a horocycle and a geodesic flow here. So the group in which these flows are happening is not the usual ASL2, but it's the ASL2. So it's a semi-direct product between SL2 and R2. We have a quotient of this Lie group by a lattice gamma. Gamma happens to be a particular lattice generated by these two matrices, semi-direct Z2. So the pictures are quite nice because you can kind of decouple the picture in the SL2 part and the picture in the R2 part. So when you do this quotient, you get some kind of non-compact surface on one side in the SL2 part, and then a torus on the other side. But the relation, because of the semi-direct product, is not just a product. And then on this quotient, we have a well-defined function capital C, which I don't plan to give you the definition of. I have it in a slide at the end in case you want to see it later. So there is a function that's in principle defined on this whole Lie group G, but it happens to be gamma invariant, so it's actually meaningful and well-defined in the quotient G mod gamma. On this G mod gamma, or in G, we have these flows. So this is the usual geodesic flow extended by two extra variables. And this psi, if you didn't have this, this would be the usual unstable horocycle of this geodesic flow. But here, since we have something in the other two variables, you can think of this as a horocycle lift. Because if you forget the R2 variables, it's a usual horocycle. So we are lifting the usual horocycle in a five-dimensional space rather than in the usual three-dimensional space, which is the unit tangent bundle to your surface. And the parameters have to be chosen carefully. So the t, the geodesic time, is basically 2 log n, where n was my initial sum, the parameter n in the sum. So this is somehow this kind of magical step where you come up with this function capital theta, and we were not the first one to do this. So this goes back to the original work of Jens in 1999, where the R2 part wasn't there, and then later papers. But there is a machinery that allows you to write this as a particular orbit under gamma, where you have a horocycle lift, and then you hit it with the geodesic flow. I should mention here that we're taking quotients on the right, on the left, and so our action is from the right. So here we are really taking the geodesic flow and then acting on it from the right by the, sorry, we're taking the horocycle and we're acting on it by the geodesic. So as t gets larger and larger, as n gets larger and larger, then these horocycles will get longer and longer and longer. So because these are the unstable horocycle. All right, so here's a picture of our quotient looks like. So we identify, the unit tangent bundle to the upper half plane with PSL2. Because of the way our gamma, our lattice gamma looks like, we have something that looks like this. So here you can kind of see in these dotted lines in the middle the usual modular surface, the usual fundamental domain for the modular surface. So this is a triple cover of that, because there is another copy here that's chopped and half to the left and half to the right, and then there's another copy flipped over down here, and then there is this thing times a torus. So this is a choice of our fundamental domain. So you can think of this thick, so this tangent bundle to this surface. This surface has two cusps, one at infinity, one at 0. The cusp at infinity has width 2, the cusp at 0 has width 1. And we select this fundamental domain in a way so that we understand very well, very, very well, what the preimage of basically a ball of radius r, the complement of a ball of radius r look like. So if I ask myself, when does theta f land in the interval r to infinity? Well, I know exactly what points in here do that. When I evaluate my function theta, remember, theta is defined on G mod gamma, and that's a fundamental domain for G mod gamma. In G mod gamma, what are the, and this is complex valued, well, it's real valued because, you know, this is real valued. What are the points that land outside a ball of radius r? And this, these pre-images will look like, well, you have to be in the cusps for this to happen. You can either be up close to infinity in the cusp and simultaneously close to this strip in the torus part. There is this horizontal strip near xc2 equals 0. xc1, xc2 are my variables here in the torus. Or you can be in the other cusp, but in the other cusp you have to be near this band and this slanted band here. And the larger the r is, the higher up in the cusp or the lower down in the cusp you have to be, and the narrower these bands will be. So we have good understanding of how these pre-images look like, because we need to understand the tails. We need to understand when is this thing large, right? So then we use the dynamical, we use the dynamics. We use the group law on this surface. So we start from, you know, or cycle lift geodesic flow. We want to somehow get rid of this x dependence that we have in this lift. So you can play with the group law and turn it into, instead of alpha plus beta x, so there is an x dependence here, into alpha minus beta, a column vector here. Then you have this kind of x dependence that you can somehow pass through. You somehow start commuting these terms, and then you end up with something that's down here. So that's the price that you have to pay to get rid of the x dependence and turn it into this way. You pick up this term, this yellow term here, which then think of, you know, beta was kind of bounded, t goes to infinity, and here you have e to the minus t over 2. So this is kind of a small group element. You want to absorb that group element into the function. I will not go into the details of how you do that. But after you do that, you end up with understanding the orbit under gamma of this element, which essentially only lives in the torus, because there is an identity matrix here, and then you have alpha beta. And I mentioned here that there is actually a trick to flip alpha minus beta into alpha beta. And this is not surprising if you remember those pictures. If you flip the picture this way, the picture were symmetric. So the alpha and the beta, alpha beta and alpha minus beta will behave the same way. But, you know, there's a computation there. So basically, now we have to understand how this function behaves when I have when it's evaluated a group element that looks like that. It's a fixed rational point in the torus, and then the usual horocycle, this blue one, and the usual geodesic. So this allows, so these arrows here are not part of step 3. These are like the new to-do list. The new to-do list is like, okay, remember in the previous picture, I knew how, like when this thing is large, but only when it's in this fundamental domain. So usually this thing will be, this G will be anywhere like close down here. So I need to first bring things back to my fundamental domain. When I bring things back to my fundamental domain, as I see here, I need to find a representation of this group element inside my fundamental domain. And in the fundamental domain, since I know how things are larger or not large in there, I need to check whether this point that I've brought, the representative of this point that I've brought back to the fundamental domain hits or doesn't hit those bands where things are large. Because that's what helps me understanding when things are large. And then since, you know, how do you bring things back to the fundamental domain? You harvest group elements from gamma, and you let them act on this green point. As you let them act, so you can see what gamma does to these points, alpha and beta. So the price of bringing your thing back to the fundamental domain is to change your alpha beta to another alpha prime beta prime, and it's done for you by the group. But because the group, the lattice, was of the form gamma theta semidirect Z2, somehow the Z2 takes care of this, you know, this alpha beta in principle was in the real line, whereas in R2, because of this Z2, you're now in the torus. The Z2 does a mod 1 in both coordinates, and you're left with understanding the action of this group gamma sub theta, which was generated by the matrices 1, 2, 0, 1, and the inversion 1, minus 1, 1, 0. How does that group act by affine transformation modulo 1 on the torus? and just check that the orbit under gamma sub theta of alpha beta in the torus actually avoids those two lines that are the only lines in which you have an opportunity to be large. So that's somehow this computation allows, which is a, we use the dynamical picture here, turns into another dynamical problem of understanding the geometry of these orbits. These are the gamma orbits of alpha beta. We need to make sure that they avoid certain lines. That's what we need to do. So let's see. It turns out, and so that's somehow the second piece of this to-do list. That's the one I've written here. We can actually compute explicitly. This was, Tariq worked this out very neatly. We can compute exactly the orbits of this alpha and beta. So all of these alpha and beta of that particular type, A, B, and M odd with the GCD equal to 1, actually belong to one orbit. So for those pictures I showed you before, each picture was one single orbit. So they all belong to one orbit. For example, the orbit of the point 1 over 2m, 1 over 2m. That's the simplest of them. And I call the orbit OM. And you can check with number theoretical consideration that that orbit actually misses exactly those lines that you want to miss. And those are the only lines that would give you an opportunity to grow here. So this is, again, the picture for m equal to 1, 3, 5, 7, 9, 11, 13, and 15. And in all of these pictures, I hope you can see that this orbit, no matter how complicated it is, it just so happens that it avoids this horizontal line and also these two slanted lines. Kind of barely, but it does. It does. So good. They avoid the lines where that's the only opportunity you have to be large. So if you avoid the lines, you're not large. And then there is a key estimate, which you'll see more about it in the talk by Tariq. We actually split the things into two pieces. If you're near infinity, if you're in this top part of the fundamental domain, and you avoid the horizontal line, or if you're near 0, the other cusp, and you avoid the slanted line there, then we can find a bound for this function, which depends on this kappa s, which I gave you very early on in my slides. This kappa s was this soup defined using the quantum harmonic oscillator with initial condition equal to f. So there is some condition here. S was some arbitrary number bigger than 1. If you assume your f's to be Schwartz, you have freedom to choose your s. If f is less regular, then you don't have so much freedom to choose s. And then you have a constant here. And this constant, if you think about this picture, somehow picks up how far are you from touching these lines. So for example, in this particular case, you're very close to the line where there will be actually growth. And so the bound that we get, the closer you can get to these lines, the worse the bound will be. So you can think of this bound, I think this quantity will grow like m, I think. And the dependence upon S is also very interesting for a number of theoretical reasons. The Riemann zeta function or Hurwitz zeta function are involved, but I don't want to go into that. Then, as a last step, I need to apply this estimate. This estimate is an estimate that I have for an arbitrary f, provided it's nice. But if you remember this step here, I had an f to begin with, but now I ended up with a slightly different f that has absorbed somehow this small element. So I need to make sure to apply this bound, not to f, but to the new f that is t and beta dependent. But that's not too hard to do. So somehow you can bound this kappa s quantity for the modified f in terms of the kappa s quantity for the actual initial f, and you pick up some extra, some multiplicative error, let's say. But then you just apply this, you get this bound, and then you still have this S dependence. So maybe I'll say a couple of words about this S dependence. S is somehow this measure of regularity for this this kind of uniform decay of the function and the quantum evolution of this function. So you can imagine that there is a one parameter family of unitary operator that starts from the identity and travels through, let's say, the Fourier transform, and then keeps going and goes back to the identity after some interval of time. And this unitary operator somehow change your f, And for all of those unitary, unitransforms of F, you want to make sure that there is some uniform decay. S measures that, uniform in this sense. It turns out that if S is too large, if you try to give bounds of how big is this kappa S, if S is too large, this kappa S is large. If S is too close to 1, this kappa S is also large, because you pick up the pole of the Riemann zeta function. So there is going to be a large value of this quantity near S equal to 1, a large value of this quantity near S equal to infinity. So somewhere between 1 and infinity, there is a sweet spot. So you can imagine you have this function that looks like this. So you want to somehow optimize over S, so get close to S equal to 1, but not too close, otherwise this gets bad. So somehow there is some kind of balancing act that you can do. If your F is short, there is no issue in choosing your F. If F is less regular, then you have less freedom to choose your S, so you cannot go too large, but typically things are well behaved. So at the end of the day, you get this bound. Let's see how I'm doing with time. Probably almost done. Yeah, so that's how you get this bound. So again, we use this dynamical representation of my quantity with some dynamical technical aspect involving this the solution to this quantum harmonic oscillator. Here is just some picture to conclude. So here I'm showing you not the plot of the absolute value, but the actual plot in the complex plane of these sums for particular choices of alpha and beta equal to 1/10 or 1/14, 1/18, 1/22 for these particular choices of parameters that we have chosen. And what I'm doing here, I'm starting again. Here I go back to the F equal to that Gaussian that gives me the Jacobi theta function, and I sample. So epsilon here is 500 to the minus 2. I sample 200,000 times the value of X, and I get something compactly supported. You don't really see the compact support in that picture, but you should see it better here. There is literally nothing outside this disk. There's nothing. There's not a single point outside this disk. There's kind of a faint. I'll try this. This probably will break everything. Here, no. How do I zoom in? Here, no. Del for X. Okay, so we'll try. It doesn't matter. It doesn't matter. So if you look in the screen here, you can see that there is nothing outside this disk. There's a faint disk here, but there is nothing outside that disk. And there is another disk here that's very, very faint, but there's nothing outside that disk. So you see here that no matter how you sample this X, in this case, I sampled it randomly, but you didn't have to sample it randomly. We have bounds for all X. You get a nice illustration of how bounded these quantities are. And if for some reason you chose alpha or beta to be 0, which lots of people have done before. Oh, let's try. I don't want to, yeah. If you choose alpha or beta to be 0, you will never see these bounded things. So because 0, alpha or beta 0 was exactly on one of those lines that will give you growth. So unless you choose alpha and beta to be in the orbit, in the gamma theta orbit of 1/2m, 1/2m, you will never see these bounded quantities. There will always be tails. So these are the particular parameters that, if you think about probabilistically, they will give you compact support. By the way, you see all of these like nice ripples in there? I do not understand those ripples. I understand that this thing is bounded. I can explain that, but I cannot explain those very, very nice ripples. So I definitely want to understand those. So that's for the future. So thank you. That's it.